Hello guys, welcome to the video. We're going to talk about the volume of revolution disk method. So you can see up at the top I've got if f of x is continuous and f of x is greater than 0 on this interval a to b, then the solid obtained by rotating the region under the graph about the x-axis has a volume with r equals f of x of this. So I wanted to show an example and kind of talk about this formula, where it comes from. So here we have f of x equals x plus 1, and we're trying to rotate that region from 0 to 3. I've drawn a quick little figure about it. So the main idea here, this is why it's called a disk method, as you can see. If you imagine taking that line and rotating it around the x-axis, you're going to get a solid, right, which basically kind of looks like a cone. I guess the technical word would be a frustrum, because it's like a cone with its head cut off. But let's think about how you would find the volume of this thing. So if you just consider one of these infinitely small disks, which have a width of dx, the volume, or really kind of just like the area of the rectangle kind of thing is, sorry, no, let's think about it in terms of the circle. Okay, so we know the area of a circle is pi r squared, right? So the radius of the circle in this case, right, is f of x. So we're squaring f of x. Okay. But then when we make it three-dimensional, the volume, therefore, would be f of x squared times by dx. So, that's just considering one infinitely small disk. So when it comes down to it, we're then taking all of these infinitely small disks and adding them up. That's what the integral does. And so you end up with this formula here, where we're taking it on that interval from b to a. And yeah, okay. So let's look at how this plays out. We have this integral from 3 to 0 of f of x squared. In this case, f of x is a line. And so we have pi out front. Okay, so there are many ways you could integrate this. You could expand it out. It's nice, I see, because inside the parentheses or brackets is x plus 1. So the derivative of that is just x. So if you either imagine doing a u substitution or actually do a u substitution, du is equal to dx, which allows me to kind of integrate it like normal. No, I don't want to do that. So I'll do, it allows me to get the integrand right away. So x plus 1 cubed over 3 to 0. Okay. So this is doing a u sub without actually doing a u sub. Okay. So now we just need to plug into our bounds. So I've got 4 cubed over 3. It's nice when you have 0, because that goes away, so it just left with this. 4 cubed 64. And we get our answer of 64 pi over 3. Okay, so that's an example of the washer method, or not the washer method, the disk method, because, yeah, we took that infinitely small, really it's a cylinder, all right, we call it a disk, but, you know, that's where that formula comes from. All right. Okay, so in the next idea is basically the same as what we were just doing. So, you know, we're considering these disks. So just in this case, we have two functions. So think of this just like where you're finding the area between two curves, just like we did previous on Friday. All right. So, um, well, in this case, we have the outer radius of the disk, okay, just like here, but now we're kind of hollowing out a little bit of the disk in 3 dimensions, and we're squaring that inner radius. So same idea, same principle. The dx is still the width of that infinitely small disk, and the r squared is still the radius, so you still have the functions being the radius. Okay, so this is, of course, if we're rotating about the x-axis. So we take the r squared of the outer and the r squared of the inner. Okay, now be careful. This is not the same thing as squaring the subtraction of the two, or you're squaring both functions. Okay. All right. There are some other cases to consider. So A here is the one that we did in the first example. B is exactly this formula here. So we have the subtraction problem of the two and squaring them and rotating it there. You may also have to rotate around C. All right, so a given um, horizontal line. And depending on whether or not it is above the two functions or below the two functions, it will change slightly. Yeah, so, uh, yeah. So if in the other cases, what we have are we have to modify the radii. So in this one, where the c is above the two functions, we want to do c minus g of x, okay, as the outer radius. And your inner radius is c minus f of x, okay? And that's just because f of x is closer here, and g of x is further away. Okay, so it's you know, you're imagining rotating around this one. Okay, here your f of x becomes your outer radius. So we're going to take f of x, subtract the c, and here g of x, we're going to subtract the c here. Okay, so you're more typical to encounter problems of the first and the second type. These ones are a little bit more challenging, and a bit harder to remember what exactly to do. But you just want to keep this in mind. So, for example, 14 here, which of the integrands is used to compute the volume obtained by rotating r about y equals 9. So we want to think about our outside function. So our outside function is the furthest away. So f of x here is furthest away. And, okay, so this is the same as this one. Okay, so our outer function is g of x. In this case, hold on. In this case, it is f of x. No. Sorry, it is g of x. That's just harder to see. So g of x there, and the inner function is f of x. So that would mean that what? So we want to do c, again, c minus g of x. So c minus g of x. So 9 minus g of x. And then 9 minus f of x. So this one here. Okay, and these two right out because we're adding, right? It's just a matter of which one is first, and the outer one is first. Inner one is second. Okay. So the other example that I wanted to go through was sketch the region enclosed by the curves. Describe the cross-section perpendicular to the x-axis located at x, and find the volume of the solid obtained by rotating the region about that. Okay. So I'm going to sketch both of these on my graphing calculator. And I'm going to go zoom standard. All right. So this is kind of a classical example. We got your kind of two parabolas, and oh gosh, let me try that again. So you got one kind of going this way, one going this way. So here's the area I'm interested in. Okay, and we want to find the volume. So I'm just going to set this up. Okay, so we have pi. Which one is on top? Well, so the top one is going to be the upside down parabola, which is y equals 10 minus x squared. And this one on bottom is the x squared plus 2. So my outer radius is, let's see, x squared plus 2 squared minus the inner radius, which is 10 minus x squared squared. And I'm running another graph there, but that's okay, dx. All right, and so we would, the other thing that we would need to do is determine the intersection points. You can do that on the calculator as well, by finding intersect. And I believe it's probably the same on both of them. It looks like 2, 6 is where they intersect, so probably from 2 to -2, but let me just double check. So check the other side. Yeah, so it looks like it's going to be 2 to -2. Again, I'm just looking at my TI-84. I put in both of the functions. I use calc, and I hit intersect to get the intersection points there. I would then go, you could use fnint to integrate this, or you could actually square things out. It would be an ugly problem, though, to do it by hand. Okay. All right. We'll end it here. Thank you, guys. If there are questions on anything that I talked about in this video, make sure you let me know on Zoom, and we'll talk about it there. Have a great day. and take care.